From DataStax, this is the Distributed Data Show podcast. And hello, everybody. Welcome to another episode of Graph and Code with Denise and David. I am David Jones-Schlardy, and joining me, as always, is the extremely intelligent Denise Gosnell.
Oh, thank you so much, David.
And, I try to come up with a new set of adjectives every time.
I can see you thinking through that, actually.
You know what it was? Is I had to remember what I was going to say for you this time, because I want to make sure they're different every time. Yeah.
Well, yeah, no, I appreciate that. But shout out to you, David. You're incredible. I love doing this with you every week. This is such a very fun dynamic to get to have as we learn all of the insides and outs of working with graph data in Cassandra. So
yeah, maybe we could just do a whole show on positive affirmations between each other. What do you think?
I don't think anyone would watch that.
Okay. So today, let's see. So last week you brought me through chapter 5, exploring neighborhoods. And we did some fun things there, right? Now, I again, unless you give me homework to go through the future ones, I tend not to look at the material on purpose. I did just briefly take a look at chapter 6, which I believe we're going to drop in today. I'm kind of excited because this is where we're going to start getting into some of the IoT sensor stuff, which is fun.
Yes.
It's actually really fun.
Yeah, so what we are doing in chapter 6 and 7, I think, is kind of like the author inside of writing this. It was my favorite example of the book because it was a new use case that we had stumbled upon and wrote about as a part of our work. So I'm excited about this, but I know that the early reviewers they have other examples that they like better. So we'll just kind of have like an author highlight of their favorite example as we go through this. So for those of you who are maybe joining for the first time, welcome. We love having you here. For those of you who are coming back, glad to see you as well. As always, David and I are both monitoring questions on a few places. If you are looking for asking us questions as you go, absolutely ask questions at any time. We are always watching on YouTube at DataStax Devs, and we're also watching on LinkedIn because we're getting a ton of comments there. So make sure you keep them coming because David and I are going to just interrupt each other and make sure we get your questions in.
Oh, totally. And speaking of that, I see the first comment is from Frank, our friend Frank, over on LinkedIn.
Nice.
Is it Demone? Frank Demone? Tell me if I got that right. But yeah, we've been talking with Frank a lot actually over the last so many weeks. Kind of met Frank through the show. So hi again. Just want to give a shout out there. And with that, I have a feeling you probably want me to share my screen so we can go do the stuff.
Actually.
Oh.
Actually.
Oh no.
I think we're flipping it up this week, right?
Oh.
Yeah, so I'm gonna, sorry for that, for that
Okay.
interjection.
Okay.
I got a little excited.
Excited is okay. That's good.
Yeah, so for those of you who are joining at this part of the journey, so the first few episodes, we have been talking about a financial use case with exploring neighborhoods of graph data. We are making a hard pivot today, and we're gonna introduce a brand new use case. We're gonna be talking about time series graphs in self-organizing networks. And what a better way, in my opinion, than to introduce this to David, than to just to kind of honestly walk through some of the book images that we set the stage of the type of problem that we're solving. So we're going to flip it around, and I was going to start with some screen share to get started, if that would work for you.
I'll go for it. Yeah, I'm excited.
And let's make sure we're here. Let me know if you can see this, David.
I can so far. I'll just wait for it to catch up on the streams.
Okay. Yeah.
So the screen I have is really small in the app that we're using. So just the live stream is going to have to be where I see it in full size.
Okay, great. Yeah. So I mean, as we're setting that up, as David and I just mentioned, we're starting a brand new use case today, and we are talking about time series graphs in self-organizing sensor networks. And so I wanted to set this up so that we had a much deeper dive into the example, David, before we start going into the traversals that you're going to be closing with today. So the plan for today is we're going to introduce this type of graph. I'm going to walk through some of the data in the schema, and I'm going to teach David about this type of graph, where you see it, how it's used for being proactive in failure scenarios for the power grid in the United States. And then David does have the traversals queued up to get started. So does that sound good, David?
Sounds good to me.
All right. So what this example brings together is probably one of, in my opinion, the most beautiful intersection of different shapes and types.
Oh, hey, Denise, real quick.
Yeah.
Hey, Lynn was just letting us know that it's really small. So if you can, to zoom in on that as much as possible. Thank you, Lynn. Thanks for pointing that out.
Yeah, great. And I have it full screen. So I'm curious if it was really small on the initial or if it's really small after the screen share. I think right now it's as big as we can go. So I kind of been at a loss of where to go next. Do you have any advice, David?
What are you using to present with?
So we are just looking at basic Google slides here.
If you're in Google, you could try, if you're on a Mac, you could try Command Plus to see if it'll zoom in on the slides themselves. We are. There you go.
Yeah, I think we are about as large as they're going to be.
All right. We'll just have to go for that.
All right. Yeah, so, and I'm watching on YouTube and on LinkedIn, so I didn't see that one. So, and Kamal on YouTube is saying it seems to be good now. So keep us coming, guys, if it's working. So
wonderful, thank you.
But yeah, so for this example, what we are going to be taking a hard pivot from talking about neighborhoods of data into a time series graph. So let me walk through in detail where this graph exists. What you're looking at is a map of Seattle, and there's two types of vertices that are on the map: the blue diamonds and the orange asterisks. The blue diamonds represent cell phone towers around the Seattle area, and they are accurate. They're the real set of cell phone towers plotted by their lat long. And the orange asterisks represent homes and businesses, where at every home and business, you need to know how much voltage is being used, say, every 15 minutes by that home or business. Now, obviously, there's a lot more homes and businesses than I'm showing on this plot right here. But just for this example, I wanted to show a subset so you guys could get an idea of how this kind of lays out in Seattle. This dynamic graph comes into play between the communication of how a sensor, the orange asterisk, sends the voltage levels back to the centralized database at the power company. And these orange asterisks, or these sensors, have two jobs. First, to collect the reading, and second, to communicate it. The collecting of the reading we're not going to get into, because that's getting into some of the electrical engineering of how these sensors work that I am not prepared to talk about. Where you find a really interesting dynamic time series graph is in how these sensors communicate that reading to the centralized database. Here's what they do. Once they have their payload of how much voltage was used at a home or business, they send it to a nearby available sensor. It can be another sensor or it could be a tower. And they change it every single time. So you can think about a sensor, say, collecting its voltage level and then passing the data to an available sensor, maybe to its left. And maybe next time it passes it to an available sensor to its right, or there was a tower right in front of it and it just directly connected and sent the payload to the tower.
Oh, so something, okay, so that's interesting. So it's not just like you have like some hub somewhere and every one of these sensors is talking to this one particular hub or something. It's kind of organic. It feels like it could be two sensors that are essentially just around it.
Yes, exactly. Okay. And I have a video I'm going to show here in a second. I'll go back, but absolutely, David, it's different. It changes every time.
Okay, cool.
So you can kind of think about it. Well, if the goal is for this sensor to get its payload of data to a tower, it's very interesting to know the path that it took to get there.
Yeah, I was going to say, this is just how you explain that, and the fact that they connect the way they do kind of almost immediately made me wonder if you were going to go there with the graph.
Yeah, absolutely. Absolutely. And why do we even want to go there? We need to go there because these power companies have to remain in compliance for different types of voltage levels throughout their network.
Okay.
And they also have to be able to be more proactive to mitigate failure scenarios. So this entire example over the next 2 chapters is going to be about the second use case, being proactive to mitigate failure scenarios.
Okay.
So I do think that the best way is to kind of see this in action. So to the point earlier about someone who let us know that it's hard to see this, I'm going to go ahead and just use the video on my laptop instead of in the slides, because I think it's going to be zoomed in a little bit better. So I've switched over, and what we have is we just kind of have a minute of what it looks like for this graph to be sending data from its sensors to the towers. So we have the same graph of Seattle. We've changed the visualization. The blue circles represent the cell phone towers. The white circles represent the sensors. And we're going to slowly watch sensor communication build up over about a minute of this video that we've created, just so you all can see this here. And David, what you're going to first start to see is that some sensors are sending their data to other sensors. And those are the lines and the edges you're starting to see build up on this graph of Seattle. Following it so far? Mm-hmm. Yep. So what we're eventually going to see is that we're going to have a tower fail. And that tower is going to fail kind of in the center to the right of downtown Seattle. And when that tower fails, you're not going to be able to send information to that tower from those 3 adjacent vertices, because they were the ones that were communicating with it.
Right.
Those sensors use the network to communicate to a different tower, so they're back online. And eventually, once that tower does get fixed, you're able to reestablish a connection to that tower. So the big question for this entire chapter is, for any one of these towers, if that tower goes down, what sensors are going to be at risk for not being able to connect to the network?
I see.
And it's not exactly what you think it would be. So that's why it's a very interesting question. So what are you thinking, David? Like, any questions about this graph, or how this works, or why it's, I don't know, really cool?
Well, I could see a case where, as you know, if you with this many devices, right? It's the same thing with distributed systems, for that matter, right? You know, if as you increase the number of devices that you have, you are also going to increase the number of potential failures that you have. And it seems like when you have an IoT network like this with all these devices, there is a very solid chance something somewhere is going to fail, and you need to ensure that it's set up in such a way that you can still continue to communicate regardless of that failure. And
Absolutely.
so I feel like that's kind of what we're teasing out here, right? Because again, going back to that simplistic example I had before when I asked my question, if you just had like individual hubs that their sole purpose was to connect these things up and you lost one, now you've got a bunch of single points of failure, right? That seems like that's not very robust, where it feels like by the nature of this sensor network, and the fact that they can communicate through other sensors in their devices, that there's going to be like a natural, I don't want to say healing, because you're not fixing broken sensors, but a natural ability for communication to still occur, even if you lose certain towers or whatever. So I'm curious to see how this is going to play out. You said something though in what, in this proactive thing, what happens if I lost a particular tower? Will that then say, how will I know what sensors are affected? Right. And that kind of implies that, are they affected in such that they can't communicate at all? Or are they affected in such a way they're just going to divert to another sensor? And I wonder if that's actually part of what we're figuring out, right? Because if I was building something like this, I'd probably want to ensure that any sensor had more than one path.
Exactly.
Okay.
You just named the entire point. That was perfect.
Oh, great.
And by the way, we did not set this up, so that's awesome. So, David, everything you just said is exactly how the largest power companies in the United States think about this problem and why they came to Cassandra to solve it.
Oh, very cool. Okay.
So the questions that you were walking through just now about understanding how to, keep failures from taking down this network. The network, from their perspective, it's not a network of Cassandra nodes. Their network is the network of towers and sensors.
Okay.
And so they're trying to understand different failure scenarios to see if they can reduce the carbon footprint, as an example, of the number of towers that exist in cities or in different areas of the United States. So they're looking at this to how to optimally place towers. How do they optimally schedule maintenance of towers, because you have to take a tower offline. And if you do that, which homes and businesses are no longer going to be able to share their voltage levels into the network, or which ones are at risk of not being able to share their voltage levels, because they are required to report voltage levels on a certain interval, and they have to get that data.
Interesting. Okay.
Yeah. So absolutely, everything you just mentioned is all about why this is very important. And to your second statement, yes, the key is the number of paths that a sensor can take, or that a sensor does take, to get to a tower. And when you mention that, I switched the screen to this view of the failure event. And what you're seeing here is the red tower failed, and these 3 nearby sensors were the sensors that were at risk of not communicating their data, because they were sending their data through a small path to the red tower. And so from here, at this point, as the sensors are discovering new communication paths, their status does return to green because they sent their payloads to another nearby tower. Does that make sense?
Yes, it does. And you see me in a weird, you see me in a weird angle messing with my thing, because my phone camera decided to die.
Nice.
And so I'm listening to you, and I'm trying to work with that at the same time, and I'm not doing the best job of it. But no, I totally get it. I see what you said there. And so I have a feeling we're probably going to explore that whole process through our chapter 6 work in the notebook with the graph.
Yep. You named it. You've got it.
Awesome.
Yeah. So for this example, I feel like the crux of the problem is to essentially now translate what David and I see into code, right? So we need to translate and understand exactly what a failure scenario means to these power companies, so that we can figure out what risk means and all of that. So that's the plan. And what that's going to come down to is understanding how to walk through these trees of data. So the reason this is all together in another type of example is because the way that this graph is formed, it forms what we would call a hierarchical graph. And these hierarchical graphs mean that you have things called roots and leaves. And David, let the puns begin, because mathematicians are funny.
And by the way, if you want to provide a pun in the chat, please do. We will read your puns live, as long as they're not.
Puns are welcome. Puns are very welcome. We want to extend the branch to you to be involved. I'm sorry.
Oh, that's funny.
Oh, man. Okay, so when we talk about hierarchical data having roots and leaves, what we're talking about is that you have data that starts at the top, and we call that the root. And this is a tower in our examples. And this root has layers of sensors that communicate to it. And as you go down, the sensors are the leaves. So we need to start, and we need to kind of ask questions that understand how to use this data as you walk from towers to sensors in a hierarchical fashion. And what we're looking at here is we're starting to break down the question to really dig in and understand, like, what does risk or failure mean in this network? And we've reverted back to the Python plot view of this data. And what you're looking at here is a red tower that is near the Seattle airport. And I'm actually giving you the answer. I'm giving you the final answer that exists at the very end of chapter 7. And I'm showing you, David, the sensors that were at risk. So if I go back and I ask you, hey, this orange tower is about to go down, which of these green sensors are going to be the ones that are at risk? I don't know. When I first started working on this problem, I thought it would have been the sensors that are closest to the tower.
Right.
But it turns out that because of the way that these self-organizing networks form communities and essentially form communication paths, for this window of time when we were looking at this data, it turns out that the sensors that were at risk and the ones that had communicated directly with the tower that is red and went down, it's the orange ones, and they kind of extended all the way into the Lincoln Park area. And there were plenty of options for them to communicate via Harbor Island or White Center. But it just so happens that this orange network was the network that was communicating with the tower at the airport. So this is the answer to everything we're getting ready to go do.
Yeah, that's really, because that's, at first glance, that's not what I would imagine that would look like at all.
Yeah.
That's interesting. So are we going to, I'm curious though, I don't know if we will explore the why of that through the graphs, or is that just an implementation detail on how the sensor networks are deployed or something? Do you know?
So it is an implementation detail on how to configure the individual sensors. And that's where we work with our customers to give them the information. But we do want to provide the why, though. We want to provide, why did this sensor over here, why didn't it have another option, or what are its other options? And so actually the why is what we're going to figure out in Gremlin with our traversals.
Very cool. And by the way, I just want to point out that Frank on LinkedIn said, this is really useful and valuable. Among cities I have worked on designing is Rio de Janeiro. So that is cool.
Oh, fantastic. Thanks, Frank. Glad to hear it. I have seen very similar examples like this for different city planning or any type of physical infrastructure planning. When it does come to roads, when it comes to tower and sensor placement, you can think about the edge network that needs to be created in order to allow for 5G. There's a ton of different ways that this is applied. So great question. Thanks, Frank. So what we're going to do is we're going to break down questions. And David, we're going to spend a lot of time framing questions before we start looking at code. Okay. Because from my perspective, in order to really understand this, we want to walk through the questions we're answering and start to break them down into something that you can translate into a Gremlin query or into a graph query. And our questions, from my perspective, they're still way too big. So the question we're going to start to break down is which sensors are at risk if this individual tower goes down? And I see that as two sub-questions. First thing is, for this individual sensor, which sensors sent information to this tower? Or, I'm sorry, I said that backwards. Let me try that again. For this tower, for this individual tower, tell me all of the sensors that sent information to it. So now I'm going to end up with a list of sensors. Say 10 sensors, and these are the 10 sensors during a time window that communicated with this tower. After that, we want to say, okay, for each of these 10 sensors, what other towers did they communicate with, right? And if you end up with a sensor in that list of 10 that uniquely communicates with your tower that's about to go down, that is the definition of an at-risk sensor, because it doesn't have another path in the network.
That's right. That's right. This is a wonderful graph problem, isn't it?
It is. And it also comes down to how this hardware is implemented. These sensors are Markovian, is what we would call from the data science community, which it just means that they're very naive. They just communicate with what's available. They don't make an intelligent decision.
Interesting.
Yet. So we're gonna go one layer further, and let's look at pictures of this graph, and we're gonna walk through it so that we understand how to use the data. So we're zooming into downtown Seattle. We've got 3 towers: the Westlake Tower, the First Hill Tower, and then the Seattle Tower. And what we want to do is we want to actually walk through how this would look to answer some of these questions, and we're going to pick specifically the Westlake Tower. And we want to understand, well, which sensors sent information to the Westlake Tower. And when you're doing this, pardon for the flipping, I wanted to see what was next. But David, when you're doing this, you have to think in neighborhoods, just like we got done doing in chapter 3, 4, and 5, right? So if you look at the Westlake Tower, we're going to walk backwards. And we're going to say, okay, well, which sensors directly communicated with Westlake? And so I'm going to start kind of up at the upper left at A, and we're going to kind of walk clockwise. Okay. So you can see that A directly communicated with Westlake. Yep. And then you go to the right and you see B directly communicated with Westlake, as did C, F, E, G, and D. Yeah? Okay.
Yep.
But a vertex like N did not directly communicate with the tower. It went through C. So N does communicate, but it goes through C and then it gets to Westlake. Or vertex I. vertex I went from I to F to Westlake. Or it went from I to H to E to Westlake, right? So now you see like you're getting different lengths of paths.
Okay.
So when you're walking from towers to figure out all of the sensors that communicated with it, I hope you're starting to see there's going to be some recursion popping up, right? So we have to walk out one layer. We have to walk out 2 layers. We actually have to walk out recursively until there's no more layers to walk.
Yes, because you wouldn't know, right? You wouldn't know how many layers of recursion you have.
Yep, exactly.
So, I see. Okay.
So when we start doing this in code, we're going to fix the recursion layers just to get an idea of how to use Gremlin to do this before we actually like fire up, give me full recursion and give me full loops. Because I absolutely, when you're learning how to write Gremlin code, work in steps and work one piece of your query at a time before you go for the hardest problem. So
yeah, totally.
does that make sense on how we're going to go from towers out to sensors?
Yes.
Awesome. So what that gives us now is that's going to give us like a full list of sensors to talk about. This is our full list of 10 sensors that communicated with Westlake. So now for each of those 10 sensors, we have to do the reverse. We have to say, okay, tell me where each of these sensors sent their information to different towers. So let's do that question now. We're going to start with sensor S. So you can think in reverse. We just went from a tower and we grabbed every single sensor that talked to that tower. And now for each one of those sensors in our list, we need to figure out which towers it communicated to. And this time we're going to start at sensor S, which is in the lower right-hand corner. And there's a bunch of paths, right? So like you can see S directly communicated with Seattle. And then sensor S, which is for start. It went from S to A to First Hill. So that's kind of like a path of length 2. Or you can find multiple paths of length 3. And actually, David, I'm curious, are you seeing these paths? I'd love to let you kind of take the paths and start walking through.
Well, I'm definitely seeing a path. If we're starting at S, right? You already hit Seattle on First Hill. If I go to Westlake, I see S to A to C to D to Westlake.
Yep.
It looks like, well, I guess No, I was going to say, it's not coming out of the First Hill Tower. I don't see another one going to Westlake, though.
Yep. That's the only one that goes to Westlake.
Okay.
So now we have to figure out, though, is S at risk? So like S would have been in the Westlake set to say that there was a way that we got to S.
Okay.
But what we need to figure out is, well, if Westlake goes down, does S have another tower it can talk with?
Sure seems like it.
And so like a path of length 3 or 4 to get us to Seattle. Do you see where you could find one?
I mean, if we're not going directly to Seattle, we could seemingly go through A to B to E. Yeah. Right. And there's a whole set over there, actually.
There is. Absolutely. And so that's where the flexibility and also how these sensors are constantly changing communication paths. They make it kind of a very interesting, very dynamic, and that's why we call this a time series self-organizing network, because these are always changing. But yes, absolutely. S has multiple paths to Seattle, a whole set of them, actually, from length 1 to 3, 4, 5, and 7, I think, if I did that quickly. But so there's a ton of ways for S to talk to Seattle, S to talk to First Hill. So the question here of, all right, Westlake Tower is going to go down. Is S at risk? It's not, because it has other ways to talk to Seattle or First Hill.
Right. By the way, there is a question that came in from Chandran. Are we doing BFS graph traversal?
We are doing breadth first search, and absolutely.
There you go. All right, Frank, there's an answer for you. I had the same question, Frank, by the way, because he asked, what's BFS?
So BFS is breadth first search, and breadth first search is a searching technique on how you walk through graph data. And there's 2 very popular ways to walk through graph data. They're called breadth first search or depth first search. And the only difference is if you go wide or go deep.
Yeah.
So breadth first search is going to explore your full neighborhood, and then it's going to take the most recent one and then explore its full neighborhood. Whereas depth first search is going to keep going deeper into the graph before it returns back and explores the next path. Tons of great questions for algorithms that we've had in this series. The speed and algorithmic complexity of breadth first search and depth first search are technically the same. So there is not an advantage of doing one over the other, because the overall computational complexity of both algorithms is the same.
Okay.
Yeah, great question. So that's the setup. David, do you have any other questions about like the like the type of use case or how this works with towers and sensors?
No. Honestly, I'm excited to start getting into some of the actual traversals and looking at what this is. How do we explore this with our graph?
Awesome. Yeah. And so we're gonna tee you up for that. So this next little piece here before we get to some of the first traversals that David's going to run in chapter 6 is just kind of taking a look at the data and the code. And so what I do have in our GitHub repository or through a stack, a Docker image or a stack in DataStax desktop is all of this data, which is real. So we have a real set of all of the towers across the Seattle and other downtown areas. I think it's Bremerton. Is that what's across the water? I kind of already forgot. I was just looking at the map. I just had a map in front of me and I can't remember I'm pretty sure it's Bremerton, but that's someone can correct me if I'm not remembering that correctly. But yeah, so this is what the CSV looks like. So you're going to have a partition key, which is going to be the tower's name.
Okay.
And then you're going to have the lat long. And these are the real lat longs of these towers. I also created some partition keys to name sensors just numerically. So the sensors are going to have numerical names. And what you're looking at here is an edge file. So we've talked a little bit about vertex labels and edge labels up until now. So if understanding how to make edges and stuff like that is new to you, just go with it. I think you'll see it as we go, but some of the earlier episodes I'll do walk a little bit deeper into edges and things like that. But there's two types of edges that we've seen so far. One edge is when a sensor communicates with a sensor. And the second edge is when a sensor communicates with a tower. So what we're looking at here is an example of like the top 10 lines from the CSV of sensors communicating with towers.
Right.
And you can see that here. These are going to be our edges where you have the partition key from the sensor as the first element in your CSV. We have the time it occurred as the second element here. And then the partition key for the tower is going to be the last element. And that's the partition key for towers is their name. So this is going to be what an edge file looks like. And from that, we've kind of been seeing this. We've been talking about this. This is going to be our graph model. We're going to have one vertex label for sensors and an edge label where sensors send information to other sensors. We're going to have a second vertex label called towers, and we're going to have an edge label so that sensors send communication to towers.
Right.
Super basic graph model, and there's a lot of cool stuff you can do with it. I swear, as the models get simpler, the more powerful queries start to emerge, and I think you're going to see that, David, as we go. I think the next model we get into in chapter 8 is like one vertex and one edge.
Oh, are you serious? Yeah. That's funny.
Yeah. We start off in chapter 5 with like this massive data model, and then as we go, it like gets smaller and smaller, and the queries get harder and harder.
I'm okay with that, though. Like most of the time you build it up the other way, but just throw it at me all in the beginning, and then let's make it easy as we go.
Yeah. Well, and that's, I mean, the modeling gets easier, but the queries and the answers you're trying to ask get a lot harder.
Get more complex. Okay.
Yep.
By the way, Yusuf over in LinkedIn there says, can use this use case in the retail industry, finding product categories for recommendations.
So I think it depends. For finding product categories, yes, because I can imagine that the product categories that you're envisioning are hierarchical. Like different levels of products and a type of product and then a brand, and maybe a brand has subtypes, and I can imagine that. So yes, for crawling the hierarchy of product catalogs, these exact queries work. We see this a lot also with different applications who are trying to solve multi-tenancy for data loading for, say, like employee networks or employee hierarchies. Like you've got a product that loads not just your company's employee hierarchy, but every company in the world that buys their product. But they have it in a multi-tenant application, and they need to have a query that quickly goes up and down the working tree to determine, say, the cost center for a certain bill, things like that. So yes, these queries work for any use case that looks very hierarchical in nature. So great question. The actual recommendation queries, different graph, different problem, different queries, and we get to that actually in the end, and we show you how Netflix does their.
Yeah, that's why I smiled at that part of it. Yeah, because I was like, ooh, we're gonna get there. Not today.
Not today, but no.
Just keep following.
Absolutely. In chapter 10 and 12, we show you exactly how Netflix does graph-based recommendations at scale using collaborative filtering. So.
Ooh.
Pardon me, guys. My hand caught my cord there. All right, so
I can't see you, so I wondered what happened just then.
Oh yeah, no, my hand caught my mic or my earphone cord and slammed it on my desk. Sorry about that. This is the spazzy graph hour. No. Anyways, so what we have here, the schema from the previous slide, we're using the Gremlin API and the DataStax Graph API here to show you how to make that schema, making a vertex label for the sensors and the towers. We saw some of that code in the previous example in the past few chapters. And this code we're looking at here is how you use our schema statements to make edge labels. So we have an edge label called send, and it's going to go from a sensor to another sensor. We have another edge label called send that's going to go from sensors to towers. How you feeling on schema?
It's a pretty simple schema for this case. I feel pretty good here. So
awesome. Yeah, and towards the end of our last session, so if you guys want to see a little bit more for data loading or how to get access to these scripts, I know at the last session, David did a little bit more of a tour on where to go to get the loading scripts. But essentially, here's the command that you need to use in order to load these files into their graph model. So the first one is showing you how to load tower vertices. So you use what is called DS bulk, which is the fastest way to get data into Cassandra. And we have some config options there for you to load into a graph and to indicate that it's a vertex label that you're loading into. And so that's what's happening on lines 1, 2, 3, and 4. And then lines 5 through 10, we're showing you how to load the edge data that we showed a few slides ago, loading it directly into a graph called trees dev. It's going to be for the edge called sensor, going from the sensors to towers. And the header line in the file does match the schema, and so that's why you have header true. So that's.
By the way, am I going to be loading data with the Chapter 6 load today?
Not loading data, because I think you do have it loaded up from DataStax desktop, right?
Yes, I do.
Yep, yeah, and so whenever you load it up there, it has everything preloaded for you in the Docker container. So, should be good. Last thing before I'm going to stop sharing and hand it over to David for notebooks is I want to actually we're going to do a few queries with David today, and I want to show you all what that's going to look like as an answer. And I think that's really important because when you start setting up your data and writing your first code and writing your queries, you want to make sure that the data you're getting back is expected, kind of like a little bit of an integration test maybe. So let's just kind of walk through what this data says and the answer should be, and it should be what we see when David starts to do his queries. So this is the question we're going to work with today. It's going to be from a specific sensor to which towers did it send information. So we're walking from the bottom up to the top. So today it's going to all be about the easier direction, which is walking from leaves up to the root.
Okay.
And so the first question is, from a sensor, where did it directly send information? That's going to be a first neighborhood query. And then we're going to do the second neighborhood and the third neighborhood. And once we kind of see how that shapes up, we're going to introduce the recursion needed to go from one sensor up to any tower. And then from one sensor, let's remove cycles and let's kind of format the path results like we've been doing over the past few weeks using Coalesce and Project so that we have JSON payloads that make sense to send around to different applications. The specific sensor that David's going to be working with here is going to be sensor 61002.688. And we're going to start there, and we're going to look at its first neighborhood. So looking at this image on the screen, you're going to see here in a second from the query that the first neighborhood that David's going to discover is going to be Georgetown, a tower, and then another sensor, 103.5508. That's going to be in the first neighborhood. Now you can keep walking up this image, and you can see that the second neighborhood is going to be White Center, and then sensor 106.1624, and then lastly, sensor 130.7588. And you can see from sensor 130.7588 that there are edges that go back to the leaf, and then also back to that first neighborhood. So that is where we're going to be introducing cycles, where your traversal could run forever and ever unless you tell it to ignore those cycles. So we're going to make sure that once you do hit a cycle, that result terminates, and you don't add more of those cycles into your results. Otherwise, it'll go forever.
Okay.
And then that you can see up there at the top, that's the final sensor or the final layer. So I think with that, it's I'm going to stop sharing my screen, and I think it's time for David. So
we'll flip over, and while I'm sharing my screen and you're unsharing your screen, we do have a question from Kamesh. Does Cassandra have dynamic graph capabilities where graph can be updated in place?
Yes, because a graph updating in place is just adding new vertices or new edges. So absolutely, a graph can be updated in place, and that's how I would think about that question. So hopefully that made sense, and if not, please let me know, ask again. But yes. And I think one of my favorite ways to update graphs is to use time on edges, or time on edges actually is singly the most popular way. And time on edges, essentially, due to the upsert properties of Cassandra, if you do have time on your edges and you want to walk around your graph and say, only the most recent edge, if you have time set as the clustering key and you walk out limit 1, that's only going to be the most recent edge. Clustering key descending, of course. But yeah, there's some really cool things you can do with graph modeling, knowing the power of how upserts work, or not upserts, but just the power of how updates work in Cassandra.
Okay. And real quick, Denise, Frank has another question. Are you using YouTube to manage the presentation or some other tool? We're actually using another tool called Social Live. It allows us not only some real-time editing and such, but it's also streaming out to multiple places. That's how we're streaming to YouTube and LinkedIn and Twitter and such all at the same time. So I didn't mean to plug Social Live, but that's the app we're using, Social Live.
Yeah.
I feel like we should now go to them for some ad revenue, right?
Right. Yeah. No, I think it's a great app just for getting enablement on every channel.
Yeah. Agreed. All right. So we have the Chapter 6 Using Trees in Development Notebook ready to go. Just something else to point out again, if you were with us last week, this might seem like a repeat because it is, but we are using DataStax Desktop to load this. DataStax Desktop is a free tool. If you just go to downloads.datastax.com and you'll see a little, if you follow the menus down to desktop. But what it allows you to do is there are all sorts of stacks here, whether it's just open source Apache Cassandra, DataStax Enterprise, if you want to get examples of how do I hook up to my Cassandra in C#, Java, Node.js, Python, all that kind of thing. It's there. It's like a one-stop shop, especially for developers, to get them up and running very quickly without having to worry about, okay, now I've got to go ahead and download the tarball, configure it, get a Cassandra database running and all that kind of deal. So here we're using the graph book examples. So if you would have come to it first, you would have come to a screen like this. I'm going to this little shopping cart, brings me to the stacks. I've already launched this. And what it will do is auto provision all the stuff in Docker for me. And this is also based off or coming from this graph book repository up here in GitHub. So if you go to github.com/datastax/graph-book, you can follow along. You can totally do all the stuff with us. And using desktop or using the Docker image, we'll have all the data preloaded and everything like Denise mentioned. Okay, done with my little post there for the repo and desktop. All right, Denise, what am I doing?
All right. So I'm over here monitoring YouTube and also monitoring comments on LinkedIn. So again, if you guys have any questions, keep them coming. And thanks for that tour. So yeah, so what we want to do is, since you did use the Docker image and you have it loaded via DataStax Desktop, all of the data should be ready to go. So should be, right? So let's just figure it out live if it is. What a better way than to test it live to make sure the tech that we wrote for this works. So yeah, we're going straight down to the queries because what we just did in the slides was spend a really long time understanding the problem that we're answering here in this broadcast. So now that we kind of have that understood, I think we're ready just to go straight to queries.
Yeah, and actually looking at the steps here, you kind of explained all this stuff, right? So we're just setting it up. This is, now by the way, I way zoomed in because I know in the past it's been, some folks have mentioned that. So let me go back. This looks like the schema we're working off before, right? No change here.
Correct. Yep.
And then this is just creating, now this again was already created, right? But this is just creating the very vertices that you showed us in your slide. The sensor and tower. Same thing with the edges. We're just creating these edges. And then that should bring us, now, by the way, this part here is explaining to, if you needed to preload the data, if you weren't using the Docker version, then you would actually have to go run this script. I just want to real quick, I did preload this, by the way, that's why I asked Denise, because I wasn't sure if we were going to need it. But if you download the repo, right, you'll see I am here in Graphbook Data Chapter 6, and I've got the Chapter 6 load script. So if I very quickly take a look, these are very easy to set up. I am using VS Bulk. all you have to do is change this one variable to wherever the path of your DS bulk is. Again, DS bulk is also free. And that's it. From there, when you run it, it will go ahead and populate the data if you're not using the Docker version, or if you've truncated everything and you want to reload it or something. I just want to point that out. It is really easy to set up and get going. And then with that, okay, finally, queries. This looks like one of the questions you asked in the slide.
It is, yeah. So I wanted to, when we made this, we wanted it to follow as closely to the book as possible. So when you're playing around with the data, you're getting the real story. So what we're doing in this first question is we are starting at sensor 1002688, and we are walking out to its first neighborhood.
Okay. All right. So yep, we're starting here. Oh, let me turn these on. Okay, there we go. We're starting at 1002688. Okay.
Yep. Yeah, so line 3, and basically, actually not basically, I apologize for that one. For those of you who might be new to seeing us do this, pro tip, what's happening on line 1 and 2 is the exact same thing as what's happening on line number 3. So I was just kind of showing you 2 different ways to access a single vertex. You can either use the g.b.has and store it as a variable, which is what is happening on line 1 and 2. And then on line 3, you can essentially just put that variable into your vertex parameter, and you're doing the same thing as what's on line 1 and 2. So doing both of these is not necessary. I'm just illustrating more ways to look up a single vertex in Gremlin.
I see. Okay.
Cool. So yeah, so line 3, we have our starting vertex 102,688. On line 4, you're walking out all of the send's edges.
Okay, and again, so we're starting with our sensor. And walking out the send edge here, which I'm assuming is going to find me a tower. Or no, actually, I just noticed oh, that's right. They can look back on themselves as well. So you could actually traverse or walk over send's edges to other sensors as well. Both.
And this is a really big deal, actually. And it's a big deal because at this point in the query, think about what you'd have to write in line 4 if you had different labeled edges, depending on if it went to a tower or it went to a sensor.
Right.
You'd have to add in more logic on line 4 if you wanted to say, oh, go out this send edge because I think it could be to a tower, or go out this send edge if it went to another sensor.
I see. Yeah, that makes a lot of sense. So this actually simplifies the process a lot.
It does. That data modeling decision was made to make the queries simpler.
Okay. Yeah.
But that just moves the work somewhere else. So that's what's happening on line 5, 6, 7, and 8. Okay. So on line 5, we did a ton of work in the last episode, or last 2 episodes, talking about shaping query results. I don't know about you, but I feel like my LASON. Oh, wow. My language these days is JSON.
LASON is a new word that Denise has now created. So let's please all use LASON from now on.
Right. So the LASON that we were setting up. Oh my gosh, no. So
that's great.
In line 5, I wanted to create JSON,
right?
So that my application had a properly formatted payload to send to its downstream service. And on line 5, I'm saying that the keys in my JSON payload are going to be label and name.
Okay.
So bonus question over you to David. Which line, 6 or 7, is going to be the logic that populates the key for label?
6.
Bam! That's exactly right. Just wanted to, yeah, that's a super useful tool that that I recommend all the time for project by. So for populating label, we're going to have our individual traversers on vertices. So all we have to do is use the keyword label, and we're going to inject the label of that vertex. And for name, that's where things get fun on lines 7 and 8. We don't know if it is a tower or a sensor. And so when we walked through at the end of that episode, an episode or 2 ago, we walked through how you can use coalesce as like a try-catch. So what coalesce is going to do, it's going to attempt to pull the tower name from the vertex. And if that provides a value, it's going to successfully complete the traversal. Otherwise, It's going to attempt to look for a tower name, and it's going to return none. And then it's going to fall back to getting the sensor name.
So this feels like what you were talking about. Like it simplifies part of what we're doing using the same exact edge labels, but it also moves the work somewhere else. And this feels like one of those spots where we're kind of moving the work, somewhere else a little bit. However, and I'm trying to do this in my mind, I feel like this is a cleaner solution, because if we were to have different edges, with different names, I would then have more logic, more code logic, more gremlin logic right up here before I ever get down to this point. So
Yes.
you're paying for it in one place or the other. This just feels a little more elegant.
Exactly. And the place that you just identified is absolutely accurate. You would either have to branch and format your payload twice for each optional edge label, or you handle the branching at the very end when you're constructing your payload. So
yeah, cool.
Cool. Yeah. And so then if you run that, actually, we will hopefully find our, I think we expect a tower and a sensor, right? Yep. There it is.
Okay.
So we're just, if you can remember back to that image we saw in the last slide, we're now just going to be walking from the leaf at the bottom all the way through the various levels. So let's just move on to the next one.
Chart, is it per chance?
It is in Lucidchart, and that's a great call. As you're getting to the next example, I will go grab the link.
Oh, you're going to go grab it? Okay, wonderful. Okay.
Yeah, I'll go grab the link so that everyone who's following can go to Lucidcharts. And that's a good point. In case this part's new to anyone following, we did open source all of the images that we used in our book, and you all are welcome to use them, of course, with citation. So in LinkedIn and then also in YouTube, I will repost the link sharing for our public version of all of the images that went into the book. It's on the honor system, so if for some reason you find a way to get access for editing things and you edit all the images, you'll mess it up for everybody else. But be a nice community member. But anyways, I'm putting this on LinkedIn as we speak.
Okay, very cool. Thank you.
Right. So next one. Next one, instead of just going out one neighborhood, we're going out two.
I see that. Okay.
Yeah, we only added one thing here.
Yeah. Okay.
And so we can run that one because all we did to go out two neighborhoods is we added on, what is that, line number, I think 7 or 8? Or no, 6.
Yeah, 6, line 6, right? We added another send.
Yep, that's all we did. So we were at the first neighborhood and we wanted to walk out to the second neighborhood, and there we go. That matches what we were expected. We wanted to get to white center and then those two vertices. So this is going well. And
I feel like this harkens back to something you were saying before, right? That obviously in this, we're going to build up. We're building up the complexity. I guess, yeah, we're building up a little bit the complexity of the traversal, where right now we're just using these, we're just saying, here, out, send. I'm not actually repeating those calls because there could be more sensors or devices that are past the second neighborhood that I don't know about yet.
Yes.
So it seems like this would be good if I had like a finite set of neighborhoods and I knew that for a fact or something. I could do it this way. But if I don't know that, I feel like I need some way that I can repeat through. Absolutely. And we're getting there. So we're setting it up. We're setting it up for that. Yep, we're setting it up. And so I think what we're really showing you here, if this is your first time working with a graph query language or Gremlin in specific, you need to kind of work through do the baby steps, do the first things that you know are going to work, and make sure that you can validate the results before you throw in recursion. So let's go ahead and just do one more where we walk out 3 neighborhoods. I do believe that's what's coming next. Okay, so this should look very familiar at this point. It looks essentially like the same exact traversal, except for now we have another out send. So we're going out 3 neighborhoods. Look at that. We have even more devices, right? So it's not just, I see. Yep. Oh, so in each one of these, I think I just realized something. In each one of these, let's see, we start here. We walk out, we find 103-5508 in Tower Georgetown. But in the second neighborhood, then we find another set of sensors and the white center. And then in the third neighborhood, I see. Okay, so this is like our gremlin has walked out and is walked out to a couple spots. And then our gremlin's walking out a couple more spots from there. And then our gremlin, depending on what the edges look like and, what the actual graph looks like. So it's just getting bigger and bigger. It is. And I think if we look closely in this last one, we should find in the payload, 100268. In the third neighborhood. There we go. You mean that one? Yep, exactly. So now if you think about it, we started on 100268 and we went out 1, 2, 3 and found ourselves back to the starting place. Interesting. Okay. So that's why recursion, just starting with recursion, could be dangerous, because if you just threw this into a recursive loop without any guardrails, you're going to walk forever and ever and ever
right? Because you found a cycle.
Infinite graph.
Yeah. And by the way, in my head, I was hearing Hamilton when the king is like forever and ever.
That's great. If you haven't watched Hamilton, that king is awesome.
It's great.
That's my part. By the way, hello, Venkata. Hi there. Venkata says hello, Denise and David, and I recognize Venkata from previous streams and such. So thanks for coming back. And Frank, by the way, also says, I wish I had this tool 25 years ago when I built the Parish France network and we had to be able to cope with network failures accurately. Yeah, honestly, funny enough, I can't get into much of what I was doing, but when I used to work in defense, we were doing a lot of things with Bayes networks and such, and it would have been nice to have this kind of capability then too. There was a lot of work that was done there that could have been greatly simplified, but 25 years in the tech world's a long time.
Yeah, I'm so sorry to hear back in those days, Frank, that you all you lost. He says on LinkedIn he lost Paris twice in a month, probably due to some network issues. Sorry to hear that. So we can reinvent the infrastructure of how these things communicate using graph technology. And I love all the work that you're driving in multiple countries around the world, Frank. So keep it up. Thank you so much. So don't run this query, by the way, David. Don't do it.
Oh yeah, it doesn't look like it's going to terminate, does it?
I mean, you're going to have to force quit it if you do. And the reason you're going to have to force quit it is because of that loop, right? Like the third neighborhood, you end back at the starting place. Oh,
geez. Yeah, that's right. That's right. I see. Right. This is what you were talking about here. So we're just going to keep going over and over and over.
Yeah. So that query will never end until you end up with a out-of-memory error or some other type of processing error. That's why when you are doing recursion with any type of programming language, or especially when you're running queries for an OLTP application, you always bound them by time, you bound them by depth, or you bound them by something else. Let's bound them by something else. The answer for this one, the answer for this one is that we want to remove cycles from the result set. And the beautiful part about that is we have a step for this in Gremlin, and it's called simple path. So instead of just any path and you let them run forever, let's just consider the simple ones or the ones that are not cycles. So you can run this one. And what we are going to do is and this one might take a second. So it's going to start from 102.688, and it's going to walk every single traverser until it ends up at a tower. So that's what we've done here. We translated our query from walking from a sensor out to different neighborhoods to start at your sensor and walk out every single neighborhood, and you only end once you've reached a tower.
Right.
Now, along the way, if your traverser has arrived at a spot where it had previously been, it's going to go ahead and terminate so that sensor or that actual traverser doesn't continue walking through the path or walking through.
And that's specifically because we use simple path that removes cycles. Is that true?
Exactly. And the way, that's the filter. So Gremlin steps have different types under the hood, and the simple path step is what is called a filter. It's a filter on true or false. And if it's true, it'll allow it to continue. And if it's false, it'll kill it. At least that's how we talk about it in Gremlin.
So what's really funny here is when I've used simple path in the past, as compared to like path and such, I used it, hence the name simple path, to essentially try to give me the shortest point between two different vertices, or the shortest path, I should say, between two different vertices. It didn't dawn on me that because it removes cycles, that I could actually use it to terminate inside of a loop and do it that way. That's pretty slick. That's cool.
And I think this is actually a really good stopping point from here, because at this point we have figured out the recursive way to walk from leaves up to all of the roots, which our roots are towers. So look, you can see here, like this tower this sensor has so many ways. You can see that there's even shaping results of over 1,000 different options.
Yeah, that's amazing.
So that's exactly the power of these self-organizing mesh networks within these power grid examples, because there's an expansive number of paths that sensor has to take to other towers. So next week from here, we're actually going to inspect the path object for every single one of these towers. It's great to know that this sensor 688 was able to get to Rainier Valley and to get to White Center and all of these different options. But what's actually very powerful is to understand the path it took on the way. So that's what we're going to get into next week.
Very cool. And I know we only have 3 minutes left today. I do see some questions that maybe you can tackle in the time that we have left, Denise.
Oh, this sounds hard.
Oh, let's see. Well, the first one is Kamesh. Do you have a suggestion on how to visualize the tower location data on a map in Cassandra natively?
That's a really good question. And when I had to solve this problem, as like a data engineer, data scientist, I went to what I felt comfortable with, which was, using Bokeh or other Python plotting libraries to just plot them myself. But as far as Cassandra native plotting, David, I actually would wonder if you have any advice on how we visualize geographic or geolocation data in Cassandra.
Well, funny enough, the first thing that just came to mind, a lot of the examples I've seen, funny enough, use Google Maps, where from a code standpoint, they've got a solid API. And the Google Maps will handle all the mapping for you. You don't have to code any of that part. So you literally are just feeding it the information with like lat longs and such. And I want to say one of the examples that came to mind right now, something that Daniel on the DataStax team did recently was create a geohash in Cassandra, and I believe he used Google Maps for that. I've got that repo somewhere handy. So if you give me a second, I will grab that and I will post it in there. So yeah, I think simply enough, you could use something like Google Maps to do the visualization for you.
Yeah, and even at the very beginning when we were showing the slides, the images that we have in the book actually was using the Google API to plot them.
Oh, was it really?
Yeah, it was. I forgot about that one. Great question. And I actually had imposed the Google Map API onto a suite within Bokeh in Python. So that's how I've done that. But another great question coming in, instead of terminating the walk, can we skip the vertex we've already seen and continue? And actually, yes, that is what we're doing. I apologize for maybe using the wrong words to talk about it, but they're doing the same thing. That traverser, once that traverser hits a returned spot, if it hits a return spot, that return spot's guaranteed to be a sensor. So we do want to go ahead and skip that path from being in the result payload because it's not an informative path or a path that gets us to a tower.
Alrighty. Well, I think that's it as far as the rest of the question. Oh, let's see.
And Frank, looking forward to your questions offline. For those of you who are following along, thank you all so much for coming in because we are at time today. And my name is Denise. David and I answer tons of questions on Twitter all the time. So you are welcome to tweet us and join the conversation that I'm super excited we're about to get into with Frank. So I'm at Denise K. Gosnell on Twitter. And David?
I am either David Jones Gilardi on LinkedIn or at SonicDMG on Twitter. And with that, thank you, everybody, for joining us for another of Graph and Code with Denise and David. We will see you next week. Take care.
Offline on Twitter. Someone's asking us on YouTube, where are we going? We're going to Twitter.
Yeah, you could reach out, honestly. Reach out on LinkedIn, Twitter, wherever. We're happy to take questions or do whatever, or just even respond here on the video chats, and we'll be taking a look at those as well.
Awesome. Thank you guys so much.
All right, everybody. Bye.